In this example, we're looking at the torsional motion of a shaft. The shaft is tapered. Its cross-section has a radius of 2r over on the left-hand side at x equal to 0. At the right-hand side, it has a radius of r at x equal to L. There's a concentrated rigid disk there on the end at x equal to L. And with all this information, then we are then asked to come up with the equation of motion for the system and then to write down the boundary conditions. Well, the standard form of the equation of motion for a shaft, that's going to be the partial derivative of the shear modulus G, the polar area moment J, partial of theta with respect to x, theta is the angle of rotation, is equal to the volume there of rho times the polar area moment J, second derivative of the angle theta with respect to time. So what we really need to come up with is what is our expression here for J. Well, the thing that we recognize here is that the radius of this thing, if I draw a picture of the cross-section of the shaft at some value of x, then the radius of this thing, which I'll call r is a function of x, is equal to 2r minus r over lx. It's a linear relationship between 2r on the left-hand side and r on the right. Polar area moment for circular cross-section, that's pi over 2 times r to the fourth. So this is pi over 2 times 2r minus r over lx to the fourth. So we see here that the polar area moment J is a function of x. So the conclusion that we draw from here is this is a non-constant coefficient equation of motion. You'll find out we'll need special techniques to solve the boundary value problem for here. What are our boundary conditions? Left-hand side is fixed, so theta at x equal to a 0 is a 0. Over on the right-hand side, it's a little bit more involved. As I draw this out, I've got this taper in there on the edge. I've got this disk. And we know that the torque on the end of the shaft is given by Gj partial theta with respect to x. Equal and opposite torque then exist on the disk. So for this boundary condition, we need to do a moment balance for the disk. So looking at the disk, not at the shaft, we do a summation of moments, and that is a minus Gj partial theta with respect to x at the right-hand side, x equal to L, and therefore by Euler's equation, that's the mass moment of inertia of the disk times theta double dot. And what we're going to do is write for a free response, we're going to be writing theta of t in a separable form. So if I write this as some function of x and some t of t, it says then that partial theta with respect to x is equal to the theta prime times t. The second derivative of theta with respect to time, it's going to be theta, which is just a function of x times t double dot. And as we've seen here, that t double dot is a minus omega squared t. So this becomes minus omega squared theta times t. So therefore, our boundary condition there on the right-hand side is minus gj theta prime at x equal to L is balanced out by minus I omega squared theta at L. So this would be the two boundary conditions that we have.